Okay, Mr. Anurag Dutta, are you available?
Yes, sir.
Okay, please, you may start your presentation.
Sir, is the screen visible?
Yes, it is visible.
So, hello everyone, Namaskaram. This is Anurag, and today at the National Conference on Computational Mathematics, I am going to present a paper entitled Methodology to Investigate for Optimality in the Balanced Assignment Problem. Firstly, I would like to thank NIT Puducherry for hosting the conference and my fellow audience for allowing me time from their daily schedule. So, let's begin with the presentation. So, this is a little bit information about me. I am currently an undergraduate at the Department of Computer Science and Engineering at Government College of Engineering and Textile Technology, Shirampur. So, let's begin with the introduction of the paper. The paper is about mathematical selection. So, in mathematical selection, what we do is we will have to select a particular choice from a set of such. It have always been a set of interesting field for all mathematicians. Accordingly, combinatorial optimization is a subfield of this domain, which is finding its importance in nearly many fields like operation research, artificial intelligence, and many more promising domains. In this work, we will be working on the famous balanced assignment problem and will propose a comparative analysis on the complexity metrics of computational time for different notions of solving the balanced assignment problem. Like we will work on the different algorithms that have been presented for solving this balanced assignment problem, and we'll try to compare them on the basis of their computational time. So moving on forward, this slide is about the balanced assignment problem. This is actually the problem statement that we are trying to solve. So suppose we are having k workers, W1, W2, W3 up to Wk, and an equal number of jobs, J1, J2, J3 up to Jk. Now, each worker are having their own cost of doing the job, and we will have to arrange the jobs in such a way that the total assignment cost is minimized. This is a classical problem of combinatorial optimization, as we are going to search for the optimal cost value, or in just terms, we will have to search for the permutation that will grant us a minimal cost in total. Now, there are various methods to solve this problem, like the brute force solution or the naive solution, then the Hungarian method, then branch and bound method, and many other methods too. We will be discussing about each of these methods in detail, and we'll try to pose a comparative study on that. So, this slide is about the brute force approach. The brute force approach is the naive approach that comes to our mind whenever we see that particular problem. So, the brute force approach for this problem would be like, since there are k workers and k jobs, we could run a selection on the k factorial permutations of the arrangement of jobs or like the workers, followed by a comparator to generate the minimum of the cost of all. So, in total, the total number of iterations that the approach is supposed to suffer is of the order O of k factorial. It is quite a naive approach and is perhaps going to take the most time to be executed. Now, if we make use of some approximation algorithm like Mortis's approximation or the Stirling's approximation, so we could represent k factorial in exponential terms. So it is going to be a hard problem in CS. So basically, the algorithm for solving this problem by the brute force approach is something like this. We will be given a matrix of k cross k order, and where the ij, like the index ij, would be the ith worker's charge for the jth job. Now we will have to ensure that we get the minimum cost or the minimal cost from it. Now, for that, we would be taking a list of permutations and one variable that would be storing the minimal cost. We would run a search along these permutations or the say, list of permutations, and would try to minimize the cost that is been possible. Moving forward, this is the Hungarian solution to this problem, that is the Kahn-Monres algorithm. It is a algorithm that is going to solve the problem in polynomial time, like the previous algorithm or the naive problem solution was going to take exponential time. So this algorithm would be helping us to solve this problem in polynomial time. It guarantees the optimality for the total optimal cost. Firstly, we will have to generate the cost matrix. where Mij is the ith worker's charge for the jth job. Now, from the cost matrix, we will have to select elements from each row and return the sum of these k elements. The algorithm for the Hungarian approach will be like this. Firstly, let us consider the initial cost matrix being something like this, where it would be a k cross k matrix. And firstly, we would be undergiving it a row reduction followed by a column reduction. Now, what is this row reduction? We would, in row reduction, try to get the minimum value that is possible in that particular column, and would try to subtract that from this particular row, that ith row. And in column reduction, we would be subtracting that particular value of the minimal row from the jth column. Now we will have to mark all those rows. Like, see, if we are subtracting this value, so sometimes it may be there that any particular entry is becoming zero. So if we are having any particular row or column having all of these entries as zero, then we will mark those rows or column accordingly. And if the number of lines that are been there in this particular matrix is equal to k, then we will say that we have hit the core, like we have found the optimal cost that is possible over there. Else we will have to determine the smallest entry not covered by any line. Then we have to subtract this particular entry from the uncovered row and then add it to the each uncovered column and then return back to step 3. Like, it would be running iteratively one over after. Now, it could be proved intuitively, like it is quite obvious from this slide, that if we are trying to find the minimal value from a particular row and from a particular column, they would be taking k cross k time, so that would be k square followed by this particular condition that this number of lines is equal to k. This particular condition is again going to take like k values at maximum, like k iterations at maximum. So multiplicatively we could just combine them to get a complexity of kq. Moving forward, this is about the branch and bound solution, a quite effective method to solve the hard problems in CS is the branch and bound solution. The first thing we will have to do to follow this branch and bound solution is to generate the state space tree. Now, what is the state space tree? Um, in CS, a state space tree is basically a representation in tree of a particular state, that is the total number of states or the possible states that one particular state can reach to. Like, if we are considering, for example, let's say the k queen problem, or like any k knight problem, so we could place those knights in such a way from that we could like reach to various possibilities. So these various possibilities, or the set of various possibilities represented in the form of a tree, would be the state space tree. So, after developing the state space tree with a fixed branching factor, we will reach out to some searching algorithms. Like, the searching algorithms could be depth first search or breadth first search, or something like A star algorithm, which is a heuristic algorithm. So, if we make use of the DFS branch and bound technique, then it would be known as LIFO branch and bound. And if we make use of the FIFO branch and bound, like if we make use of the breadth first search, then it would be known as the FIFO branch and bound. Well, we could also make use of Lewis branch and bound, which indeed is a heuristic technique to do the same. Algorithm 2 is a generalized pseudocode for the branch and bound approach. So, this is the algorithm for the branch and bound approach. The requirement and the ensuring is again the same. So, in this, we will have to generate the state space tree, which has been stored here in this particular format, and we will try to like get the minimum value that one can get of assignment cost following the state space tree. Now, our FIFO branch and bound algorithm is going to take a computational complexity like this. Now, the proof behind this complexity have been given in our paper, but due to the limited time frame of the conference, we can't like describe it over here. Now, for Dijkstra's algorithm, the computational complexity would turn out to be like this, and for heuristic A star algorithm, the complexity is like this. So one thing to note here is that they are taking k factorial time in order of like big O asymptotes, but it is not the same. So it is the amortized complexity, like amortized k factorial is not at all equal to like k factorial complexities is much lesser than that of the k factorial complexity. So by this we have come to a conclusion part of the paper. So this is a plot representing one of these algorithms or the approaches. So we could see that the minimal time would be taken by the A star branch and bound technique. So these are some of the references that we have made use for preparing the manuscript. So that's it. That's all from my side. Thank you and have a nice day.
Thank you, Mr. Anurag.
Thank you, sir.